In this video, we're looking at taking a binomial that is complex and expanding it using z to the n, using Pascal's triangle or combinations to generate coefficients of each term, and then seeing what sort of numbers that leaves us with. So recall Pascal's triangle is a triangle with a pattern that the entry in the previous row sum to make the next row. So we've got 1 plus 0 on either side, gives us 1 and 1. Then 1 plus 0 is 1, 1 plus 1 is 2, 1 plus 0 is 1, and this pattern continues. One, 5, 10, 10, 5, 1. And what we've looked at in the past is that these entries of Pascal triangle are combinations, and they can also be used to expand binomials. So in this case, we want to use Pascal's triangle to expand 2 minus 3i to the power of 3. So when we have to the power of 3 here, we're looking at this row with 1, 3, 3, 1 here. So we've got expanding it, we're going to get 2 cubed times negative 3i to the power of 0, which is just 1, plus 2 squared times negative 3i to the power of 1 times 3, plus 3 times 2 to the power of 1 times negative 3i squared. And then lastly, 1, because it's the last entry of Pascal's triangle, times 2 to the 0, which is also 1, times negative 3i cubed. And so what we're left with here is this is just 8, plus 3 times 4 is 12, times negative 3 is negative 36i. Then we've got 3 times 2 to the 1 is 6, times negative 3, but we've got this I squared, so we're going to end up with 3 times 2 times positive 9 times negative 1. So 6 times 9 is 54, so this ends up being minus 54. And then we have 2 to the 0 is 1, 3 cubed, if it's negative, is negative 27, but then we have an I squared in this I cubed, which becomes negative 1 as well, so it will be plus 27 times I. And so what we notice with these expansions of complex binomials is that a lot of the time you end up with a complex binomial. So we group our like terms. We've got 8 minus 54 is going to give us negative 46. And then negative 36 plus 27 gives us negative 9i. So we started with a binomial, we expanded it, and we ended up with a binomial. And it's all due to the fact that we have these factors of I, and any I squareds we can replace with negative 1. So what can we do with this? Well, in topic 2 of Unit 2, we will be exploring trigonometric identities and the different ways to prove them. It is possible to combine de Moivre's theorem and binomial expansion of complex numbers to prove some of these trigonometric multi-angle identities. So if z equals r cis theta, then de Moivre's theorem tells us that z to the n equals r to the n cis n theta. So what we can do with that is we get r to the n times cosine theta plus I sine theta to the power of n, and this then gives us a binomial that is being expanded. So we can equate this first line with the second line, and we get that r to the n cis n theta is equal to r to the n cosine theta plus I sine theta to the power of n, and we can divide both sides by r to the n. So essentially what we find is that cis n theta is equal to cosine theta plus I sine theta to the power of n. So if we have a binomial and we expand it, we can use imaginary and real components of the left-hand side to find identities of multi-angle formulas. So we've got cosine n theta equals the real components of the binomial expansion, and sine n theta gives us the imaginary components because we've got cosine n theta plus I sine n theta. Let's get some brackets in there so that it's clearer. So it may be necessary to use the Pythagorean identity sine squared theta plus cosine squared theta equals 1. So let's use de Moivre's theorem to prove both of these. And I know it looks like they're two sub-questions, but they're actually going to work hand in hand. So we've got cis 3 theta equals cosine theta plus I sine theta cubed, because we've got a 3 here, so we use that as our value of n. So expanding the right-hand side, we get cosine cubed theta plus cosine squared theta times I sine theta times 3 plus 3 cosine theta I sine theta squared plus sine cubed theta. So let's fix this up a little bit. We get cosine cubed theta plus 3 cosine squared theta sine theta times I, plus we've got an I squared here, so that's actually a minus 3 cosine theta sine theta, and then we get, sorry, this should be I cubed, minus sine cubed theta times I. I just missed that I component there when I was expanding, so that also gets cubed. And so what we can do now is for part A, we take the real component of cis 3 theta, which gives us this cosine cubed theta plus minus 3 cosine theta sine squared theta. But if we look at our answer compared to what we expect, we notice that we don't have any signs in it. So what we can do is replace sine squared theta with 1 minus cosine squared theta. That is, of course, just rearranging this Pythagorean identity to make sine squared theta the subject. So we get cosine cubed theta minus 3 cosine theta times 1 minus cosine squared theta. And so expanding this out, we get cosine cubed theta minus 3 times 1, so that's just 3 cosine theta. And then we get minus 3 times negative, so that's plus 3 cosine cubed theta. We have like terms here, we group them, we get what we expect, which is 4 cosine cubed theta minus 3 cosine theta. And we can see that up the top there. All right, let's finish this off with part B. So now we're looking at the imaginary component of cis 3 theta. So that's going to give us our 3 cosine squared theta sine theta. Notice that I've omitted the I because we're using the imaginary function, so the I doesn't come with it, minus sine cubed theta. And just like in our part A, we have no cosines up here, so we're going to replace cosine squared with 1 minus sine squared. And so we get 3 times sine times 1 is 3 sine theta, as we expect up here. And then we get minus 3 sine cubed theta minus sine cubed theta. Once again, we get our like terms. So we got 3 sine theta minus 4 sine cubed theta, as expected in part B. So this is a nice application of de Moivre's theorem to prove multi-angle identities. Thank you very much.